Yeah. So in today's session, I'll be completely discussing about the synthesis and the physical design implementation. So what previously in the first session I have explained like a backend ASIC design flow. So first is to start off with this, I'm just taking you with the agenda part. Usually what are all the things I'm covering. So I'll just list out here. So first I'll be completing with actually what is the synthesis, the introduction or overview of a synthesis, and what are all the steps included in the synthesis process, and what are the inputs required for start off with the synthesis flow. And here I am using a general synthesis solution tool. And what actually the features included in the general synthesis solution tool. Upon that, I'll be taking up the complete synthesis flow with the general synthesis solution tool, and along with that, I'll be taking up the pictorial representation or how we were generating the power performance area reports, or even with the how we were generating any outputs, like it might be gate level netlist or it might be SD files. Because further those two input files will be taken as a primary input for the physical design implementation. So along with that, once after completion with the synthesis, we will be moving on towards the physical design flow. Again, the start off with introduction to physical design, and then overview or inputs required for the physical design process. Then I'm implementing. And as I have already told, the physical design process includes again the 5-stage processes. It's a floor planning, power planning, placement, clock tree synthesis, and the routing. All these things, each and every single stages, what actually we were doing in the each and every single stages, I'll be giving in detail information regarding these things. Once after that, for each and every stage, what and all the reports we were generating, all these things I'll be discussing. So along with that, in the before going to the floor planning stage, what and all the checks I should need to be taken care, what and all the things I should need to be taken care, that also I'll be listing here. So first to start up with the overview of a synthesis or introduction to synthesis. Usually when I am telling synthesis, so here the RTL code comes into picture. First primary input I am giving to the synthesis is RTL code. Or you can also say Verilog or a UHDL code, which I am giving as an input. So usually the synthesis is a process of converting my RTL design in a Verilog or a UHDL. So directly that into an gates, or you can also call it as a gate level netlist. So the conversion of my RTL design or RTL code into a gate level netlist or in the form of gates usually is called as a synthesis. So actually what tool used from the cadence means general synthesis solution. So the synthesis is a process of converting my RTL design or a RTL code into a gate level netlist or in the form of gate level the logic gates. You can also say the logic gates. So this is all about the synthesis process. So I'm just moving further. You can see usually the synthesis includes a 3-stage process, as you can list out here: the translation, mapping, and the optimization. So when I am telling synthesis, backend the tool will try to do these 3 processes backend for getting the for generating the gate level netlist. So at the end. So what actually the translation and even what actually the tool will do in the translation stage, even with the mapping and the optimization. First coming to the translation. So as I have already told, primary input for the synthesis is I am taking a RTL code. Along with that, here you can say first I am giving a RTL code. So whatever the RTL code I have given, that will be converted into a generic form, or you can also call it as the Boolean expression form. The complete RTL code which I have written or which I have given as an input to the synthesis, the tool will try to do or try to convert that RTL code into a generic Boolean expression form. So in the translation stage. When I am going to the tool implementation, usually we will call it as a generic. So syn generic we will say. So usually the translation means it is in the translation stage, the tool will try to convert my RTL code written into a Boolean or a generic expression form. So usually it is a technology independent. If you see once after sin underscore generic, and you can come and see the schematic view of your case, then it will be shown. It is usually a technology independent. It will be a generic form, GTEC cells you can say. So the translation is the process where I am converting my RTL code into a generic form. So the generic form, usually a Boolean expression form. So where usually my cells, usually the translation stage is a technology independent. I am not applying any technologies here. So once after moving on to the mapping, so usually in the mapping what it will do, whatever the generic form has been created, for that the tool will try to bind the standard cells from the standard cell library. So the tool will try to infer all the standard cells available from the library. So that will be binded here. So usually it will try to map the name itself says mapping. Mapping means usually the tool will try to map whatever the standard cells available from the standard cell library I am using. Here the library I am using is .lib. So usually we will call it usually the mapping stage is a technology dependent. Why means I am making use of the standard cell library available from the foundry. So that's why here the mapping is a technology dependent and the translation is a technology independent. So coming to the optimization stage, usually what happens in the optimization stage? Optimization stage means the synthesis, whatever the Genesis synthesis solution tool will try to do the complete optimization of your design based on the constraints I am giving, the predefined constraints, usually where the SDC file comes into picture. So the SDC file, whatever the constraints I am giving with respect to the targets like power, area and the timing. So usually power, area, timing. Based on these things, whatever the constraints I am giving, the predefined constraints, that will be made utilized by the tool, and based on those predefined constraints, the tool will try to do optimization with respect to power, performance, area. So with respect to the power, timing and the area. So all these things will be optimized and will give you the report with respect to power, performance, area. And also you can able to see the gate level netlist. Usually the netlist by default it will not be generated. So again you should need to make use of a write command. Write underscore HDL you will be using a command for writing out the SDC file. Writing out the gate level netlist file. Even for generating SDC also, these two files will even with the report files also. In the GUI mode, the graphical user interface mode, you can directly able to see the reports. But when it comes to the netlist reports from the batch mode, that is nothing but in the terminal. At that time, you should need to make use of the commands for generating the gate level netlist, SDC file, and even the reports with respect to the PPA, the power performance area. So these reports will be generated making use of the commands. So this is all about the three-stage processes included in the synthesis. So I am just repeating once again. Synthesis usually it is the synthesis it is a process of converting my RTL code into a gate level netlist or a logic the RTL design into a gate form. So you usually call it as a synthesis process. Again, in the synthesis process, the three stage will be taken care. One is a translation, mapping, and the optimization. The translation means the complete RTL design, whatever the input I am giving, the RTL code will be converted into a generic form or a Boolean expression, the generic Boolean expression. So usually that is a technology independent, where the GTEC cell comes into picture in this stage. So it is a technology independent. Once after completing with the translation, then I'll be moving further with the mapping. Usually in the mapping, what the tool will do means whatever the libraries I'm giving as an input, based on the library, it will try to map all the standard cells available from the library to the design. So whatever the Boolean expression has been created, the generic Boolean expression for that complete design, what are all the cells available, the standard library, the standard cells available from the library will be binded here, or the standard cells will be mapped here. Once after the mapping process completes, or a mapping step completes, then the tool will try to go for the optimization. When I am telling optimization, so usually the tool will try to do the complete optimization of your design based on the predefined constraints, the SDC constraints which I am giving. It might be it might be area, even with all the three target constraints. If I am mentioning in the SDC file, based on the all the three constraints, it might be related to the area, power, and the timing. All the three target related constraints, if I am mentioning in the SDC file, based on all the predefined constraints, the tool will try to do the optimization, and it will gives you the better result where you are checking the reports. That is area, power, and the timing. Whatever the reports you are getting with all the three targets, that one is a optimized one, because at the end of the tool is optimizing based on the constraints I am giving. So if you are mentioning the area, power, and the timing constraints in the SDC file, the tool will try to do the optimization with respect to your timing, area, and the power to the complete design. So this is all about the synthesis process. So these are the three major steps which is taken care in the synthesis flow. So now let us move on to the inputs required. What actually the inputs I am giving to the synthesis tool, and based on this inputs I am giving, what actually the outputs I am generating. So first, coming to the inputs, so I am giving a primary input, that is the RTL code. The RTL code which I have written. So the code which I have written, the RTL code is a primary input for the synthesis. So along with that, I am mentioning a predefined constraints. Usually we will call it as the SDC constraints, that is a synopsis design constraints. So that constraints, again, it depends on how the designer is interested. If the designer is more concerned about the timings, then they can give a timing constraints. If the designer is concerned all the three, then they can include all the three targeted constraints. All the three target related constraints. It might be a power, area, and the timing. So now one more input I am taking, that is a library. So usually here the .lib I have given, the same way .lib also, but for that again that one is optional. So that's why I have not taken that input. So currently, even when I am going to the physical implementation stage, I will be explaining about the .lib. Here, what and all the input libraries and the inputs I am taking to the synthesis tool is, first one is RTL code, then the SDC constraints, then library. So usually again the libraries, again the file extension will be .lib. So usually the again Liberty file format, where the .lib stands for Liberty file format, includes the complete about the each and every standard cells. So usually it is given from the library vendors, usually called a foundry. So it will be taken from the foundry. So based on the inputs I have given, I will be generating the outputs. One is gate level netlist. So and another one is a SDC file. So usually whatever the SDC file I am giving here, this will be my chip level SDC. And whatever the SDC I am generating from the synthesis, that will going to be a block level SDC. So what actually the difference with the chip level SDC and the block level SDC means, here before going to the synthesis, I don't know actually what and all the instances are there in the design. For those instances, what is the pin names and all. So based on the pins or the ports names, I am not well known about all those things. So that's why I'll be just taking the main ports, whether the input port and what are the output ports. Based on those ports, I am just setting the constraints. But when it comes to the synthesis, after the synthesis, whatever the SDC I am generating, that is, the tool will be trying to apply all the constraints with respect to each and every instances available in the design. So that's why usually we will call it as a block level SDC. the output SDC, the output SDC file which is generated from the synthesis, usually call it as a block level SDC. The input I am giving to the synthesis, the primary input, that is also the SDC in the synopsis design constraint file or system design constraints file, that the input which I am giving to the synthesis is a chip level. So just to need to remember which is like just a chip level means of which input, and the block level SDC if I am telling means what actually the output, how I have generated. Because again the gate level netlist and the block level SDC generated from the synthesis, again I will be taking those two outputs as an input in the physical design stage. So along with the gate level netlist and SDC, I will be generating the reports with respect to power, timing and the area. So this is all about the inputs required and the outputs generated from the synthesis tool. So I have just listed out as previously I have listed the same way, usually .lib. So in the .lib means again the complete description about the cell. It might be a port information or even the which type of cells, or even operating conditions, even power consumption issues, or even timing informations. All these things come the complete functional information about the cell. We can able to get it from the standard cell library, that is nothing but .lib. So usually it is given by a foundry. Usually it is a generated. The libraries will be given from the library vendors. So here you can say the foundry. So how these things will be generated means again we will be going to the full custom. From the full custom they will be using some additional tool for generating these libraries. As you can see, I have just listed here the liberator tool. Usually the liberate is a tool which is used for generating these libraries in the full custom. I have just given the sample of the liberty file, that is nothing but a .lib file. So usually we will call it as a timing library. So .lib is called as a timing library. The first you can able to see the unit attributes, what actually the units taken for the timing, voltage, current, and even with the resistors, power, or even with the capacitive load, and even what is the temperature, voltage, operating conditions used for the design. All these informations at the top itself you can able to see. So once after that it will give you the each and every cell, the complete description about the each and every cell. It might be the pin direction information, or area information, or a power information, timing information. All these things you can able to see from the .lib library. That is nothing but your timing library. Here I have just taken the same example. One buffx2 I have taken. The name is buffx2. The cell name is buffx2, where x2 is the drive strength. So usually x defines the drive strength of my cell. And along with that area information, the cell functionality, and even with the pin direction and all will be given. The area information, power information, and along with that the timing information will be given here. And whatever the area and the power information will be given here. Based on these values only, at the end, the tool is generating the area report, total area report, the total power report. So how I got those area values, power values means based on these libraries only, and based on each and every standard cell values with respect to power, area, and the timing. So here one more input, that is a SDC. Till now we saw with the library, then the technology library, then I am moving further with the SDC. So as I have already told, so usually SDC stands for synopsis design constraints or system design constraints. So usually here I will be mentioning the constraints based on the targets like area, power, and the timing. Based on the specifications, based on the designer specifications, we will be writing or we will be creating the SDC file. Usually this is a chip level. So usually who will be creating this SDC file usually call it as a chip level architecture. So you can usually whatever the SDC I'm writing usually called it as a chip level SDC, and it is also one of the primary input for the synthesis process. And as you can see here, I have listed out some common SDC constraints based on the timing, even you can say some timing exceptions, even with the power, and even some design rules. If I have any design rules in the design, I'm checking based on that, and even environmental. If any related to the environmental conditions I am concerned, that time we can just set with the same way. Even with the area, timing, all these things, all the three targets, predefined constraints you can mention in the SDC file. So it again depends on the designers how they are interested to write the SDC file. So based on what and all the specification they want to write out the SDC file. Usually at the starting they might not be knowing the clock period and all. So usually they might be having the frequency. Based on the frequency, they will be calculating the clock period and they are setting the clock period. So with the help of clock period, they are also, along with that, they are setting some constraints. So as you already know, T is equal to 1 by F. They can calculate the clock period. They can calculate the period based on the specification. From the specification, whatever the frequency they are taking. This is all about taken care in the constraints file. So all these things will be written in the constraints file. So when I am telling the constraints, usually the tool will take by default the timing units mentioned will be in nanosecond in the constraints file. The tool will be reading the constraints, the time unit will be in the nanoseconds. So this is all about the inputs required for the synthesis process. First one is RTL code, the timing constraints, or you can say predefined constraints, and along with that I am making use of the technology library, that is a .lib. And even you have the options to set a .left also. So usually .left means again library exchange format that will be including the complete physical information. So physical, when you are going with the physical synthesis, at the time the .left file you should need to give. So but when I am taking with the logical synthesis, the .left file is optional one. So now I am just moving to the synthesis solution tool. So it is a next generation tool, and usually it includes the RTL synthesis and the physical synthesis options, as you can see in the features. So usually the genus RTL synthesis and the genus physical synthesis. So logical synthesis, as you can see, the basic one usually we will be doing. So what are the primary inputs I am setting? Based on that I will be checking. So that is a logical synthesis. If I am going further with the physical synthesis, so in the physical synthesis where the .left comes into the picture, along with that one more file I'll be giving as an input. That is usually called it as a .def. So usually design exchange format. So design exchange format file. So that usually includes the complete physical information till a floor planning or till placement stage. So that the physical information again I am coming back to the synthesis and I am reading those inputs, those files as an input. So usually that will be taken care with the genus physical synthesis feature. The genus usually we will call it as the physical synthesis. So again I have two more features, one with the DFT, design for testability. So where here if I have any, if I want to test my circuit, so at that time I'll be adding some scan chain insertion. Based on the scan chain insertion, I'll be testing my design. So again, I'll be going with the synthesis with DFT. So I'll be setting up all those commands in the synthesis script, and I'm generating the gate level netlist. And again that I am further taking for the next stages. The same way, the genus low power solution. So usually here also, if the designer is more concerned about the power optimization, then they can go with the genus low power synthesis solution. So here again, the additional inputs, what as I have already told, the power intent file. So the power intent file and even the switching activity file. So those two comes into picture in the low power synthesis solution. So these are the few features which are available from the Genesis synthesis solution tool. And usually it will deliver up to a 10x boost to the usually 10x boost instances in the RTL design productivity if you are checking. So with up to 5x, usually 5 times faster turnaround time. So as you can see, for compared to the previous tool. So usually the older tool was for synthesis. The older tool used was the RC compiler. Now the Genesis synthesis solution tool has been used. That is a upgraded one. So the new advanced one, you can say. The new tool has been used for the synthesis solution, the synthesis process. That is Genesis synthesis solution tool. The older version tool was RC compiler. Before you might be used a RC compiler. Now that has been changed to the Genesis synthesis solution tool for the synthesis process. So till this point, is there any doubts, participants?
No, madam, you can continue.
Yeah. Any queries are there, means you can just unmute yourself. I'm just taking you with a startup with a flow. How I am going in the tool execution part. So first, I'll be setting up the library. So in the library, as I have already told, the technology files which I am setting is .lib and the .left. So if I am going with the logical synthesis, then I should need to go with the .lib. If I am going with the physical synthesis, at the time, both the tools, both the technology files need to be set. So here, if I am going, while means physical synthesis means I should need to have a physical databases. So I given physical information about each and every cells from the standard cell library. So at that time, .left file comes into picture. The .lib is liberty file. Usually we will call it as a timing library, and the .left where it stands for library exchange format file. So the library exchange format file. Usually it includes the complete physical information about the cell and even whatever the layers I'm making use in the layout platform for the routing for a routing. So at that time, the metal information we will be getting with this .left files only, and even the complete abstract view, the complete abstract view of my standard cell will be available in this .left file. So first I will be setting up with my technology files. If you have any cap tables also, the cap table files generated, or from the folder if you have a cap tables, then you can set up cap tables also in the synthesis in the library setup only. You can just give the .lib, .left, and then the cap table file. So all the three files will be set up in the first stage itself, the library setup option only. So once after I have set it up with the libraries, then I'll be moving further with loading the RTL code. So here we can load a Verilog. It is supported for both the languages, Verilog and the VHDL. So RTL code I am loading, and once after that I am elaborating the design, and after that I am setting a one more input, that is a constraint, SDC constraints. So here I have shown in the flow. I have just mentioned the timing constraints. Why means usually you can say the STC, predefined STC constraints. Here I have just mentioned timing constraints because I have written the script file including only with the timing constraints. So that's why I have just mentioned as a timing constraints. If you are including area constraints, power constraints, and at the time you can just mention as a predefined constraints, or you can mention just constraint. So I have taken here timing constraint. Don't get confused with the indication given here. The timing constraint means I have just mentioned only the constraints based on the timing. So the target I have set here with timing. It is not only even we can set the constraints based on the timing, or any constraints related to the power, All these things, all these constraints will be mentioned in the constraints file. So once after setting with all the three inputs, library, article code, and the constraints file, predefined constraints, I'll be trying to start up with synthesis process. So usually previously, as I have discussed, with a three-stage process. First one, translation, mapping, and optimization. In the technically, we were telling translation, but when I'm coming to the tool execution part, usually we will say generic. So first, I'll be trying to usually, if I'm doing a synthesis in the synthesis stage, I'll be first going with a generic, then mapping, and then optimization. Once the generic syn generic completes, then I'll be moving with the syn mapping, and once after the syn mapping, I'll be moving further with the optimization. So all the three processes will be taking care in these two steps. Once after that, I'll be generating the outputs. So, and along with the outputs, I'm generating the log reports. So, I'll run with the power performance area report, power timing area report. So, when I'm invoking the synthesis tool, so when I'm whatever it may be, when how many times I'm invoking the synthesis tool, backend it will generate the two log files, one with the genus.cmd, usually the genus.cmd, which will give you the complete list of the commands which I have invoked in the terminal. So whatever the commands I'm executing in the terminal, those complete in the commands I have listed are typed in the terminal, that will be listed in the genus.cmd file. So the same way, one more file will be generated backend by default upon invoking with the genus tool, that is a genus.log. So genus.log, it will include the complete execution summary. It will include the complete execution summary. So the complete execution summary of my synthesis solution. So the synthesis process, you can say. So all these things will be checked at the end with writing out the outputs along with the gate level netlist and the SDC file. So this is all about the synthesis flow. So I'm just moving further how I can start up invoking the genus tool. So in the Linux environment, as I have already told, first I'll be making use of a ssh command for linking the Linux shell script. So once after that, I'll be sourcing the chsrc file, usually where my genus tool has been placed. That path will be sourced with the chsrc file. So after that, I'll be invoking the command genus, as you can see. GENUS, genus. Genus is a command I'm invoking to start up. I'll be typing the command in the terminal to invoke the genus solution tool from the cadence. One way directly for the beginners, if you are not familiar with all the commands, then directly you can invoke the genus command and start up. If you are already familiar with writing the script, or you are familiar with the commands to used for setting all the inputs, or even with the startup with the process also, then you can just list out all the commands in a single script. Then you can directly read that script. So usually we will call it as a batch mode, where the batch mode comes into picture. So I have two interface modes to run the synthesis tool. So one is GUI mode, graphical user interface mode, and another one is a batch mode. So batch mode means I directly making use of the commands and directly I'm reading out the script file. And directly loading the script file. So once after that, the tool will at the end, the tool will try to generate all the tool will try to execute all the commands I have listed in the script file, and based on that, it will generate each and every reports along with the outputs. So to start off with if you are already familiar with the to write out the script, then you can make use of the command genus space -f space. You can just give the script name. So here I have taken genus_script. It's errorless. Again, you can just change the name also. But the file extension should be .tcl. So to invoke the genus tool, you should need to go with the command genus. So you just give a command genus and it will invoke the tool. It will take you to the terminal where you can able to see the genus. So in the genus synthesis tool, by default the GUI mode will not be visible. The graphical user interface mode will not be visible. To enable that, I'll be using a command GUI underscore show. So GUI underscore show. So if you want to hide that one, or if you want to see that, you can just go with the GUI underscore show. If you want to disable or you want to hide, then you can go with the GUI underscore hide option. So these are the additional comments I'm taking care in the synthesis tool for seeing the schematic whatever the gate level netlist I have generated for that gate level netlist, the schematic representation or the schematic view of the gate level netlist if I want to see. At that time you can just make enable the GUI mode and you can able to see from the GUI mode. Or even backend the files will be generated. You can just go through the backend files also. So this is all about the Genesis solution tool. So I am just coming back to the script as I have already told. So I am already pretty much familiar with writing out the script. So in that case, what and all the things I will be including in the script. First comes the input setup, that is with respect to library and the RTL code. So here command set underscore db is the command I am making use for setting up the library. So set underscore db space slash space dot init underscore lib underscore search underscore path. So lib search path. Usually I am making use of the switch lib search path. I am initializing the path for the library. The same way set underscore db dot space slash space dot init underscore hdl underscore search underscore path. So I am giving hdl search path. I am initializing the sdl search path. Nothing that I am giving the directory. I am setting the path for the RTL directory where my RTL codes are there. So usually where my RTL course has been, the RTL file has been included in that particular directory. That particular directory path I am mentioning here. One with the library path setup and another one is with HDL path setup. That is nothing but my RTL directory path setup. So these are the two comments I am making use. Once after I have given the path to the directory path, I have set it up with the directory path for our library and the RTL. Then I will be reading the directory. So then I will be making use of a command again set underscore db space slash space dot library. Mention the file slow.lib. This is the file available in your lib directory. Again, don't get confused. Here only I will be mentioning .lib also. You can just give the directory name lib the same way. You can just give a space and include the .lib. And even if you have a cap tables, then you give us some space and include the cap table also. But when I am including .lib and the cap tables, at that time you should need to include the cap tables and the left files after the slow.lib has been read. So the text I should need to include the .lib and the cap tables also. Here I have not included, so directly I am going with the logical synthesis. I just need a library, so .lib file, so I am just loading the .lib file. So once after I have read with the .lib, that is a slow.lib file which is available from the lib directory. So again the technology, again what are the library I am choosing, you have the options to set for the technology nodes you are choosing. It might be a 180, 90 or 45. It's again designer specification, how the designer is interested to implement the design based on which technology node. So that should need to be taken care here. If I am going with the 45, then you can just set the path for the 45 from the foundry. So here I have current directory only, I have kept the lib directory, so I am just giving lib directory. So if it is in foundry you are calling, then you should need to set the path from the foundry you are taking. That completed with the library loading. Then I am starting off with the RTL loading, the RTL file loading. Before loading with RTL, top module name. Whatever the top module name I am mentioning in the, as you can see here, the example I have taken is counter.v. The counter.v is my RTL file. For this counter.v, what actually the top module name I have given? That top module name done. So the counter is my top module name. I have given the counter. I have written the counter name. Usually the top module name. Once after I have set up with the top module name, I am further reading with the HDL file, or you can also call it as a RTL code file, which is already present in the RTL directory. I have already given the path, so I am directly loading the file. And you might be asking, currently I have loaded with the one file. If I have a different set of files where the submodule and the top module comes into picture, I have a one top module, and along with that I have a two or three submodules. At that time, how I can call those submodules and the top modules? Anyway, you will be returning one top module with a .v and a submodule with a .v again. So at that time, you can just mention the top.v, and along with that, you can just insert the double quote only. You can just give us some space and mention the blocks, what and all the subblocks you are including. So as I have mentioned, counter.v, if I have one more file, then we giving us some space and including that particular the .v files. Insert this double quote. So that's how I'm setting up my input files for RTL. If I have a subblocks or subblocks in the design. So currently I have only one RTL code file you can able to see. That's why I'm just taking double quote with the file name, that is account.v here. So once you can also say the RTL code file I have loaded. So you can make this in the dollar design. One means directly I have already set in the top module. So directly the top module name it will call. Whenever I am giving dollar design, it will call for the top module name. So you will start to do the elaboration. Once after the elaboration, before set up with my constraints file, I am using the one unresolved. So whatever the RTL code I have loaded, whether that is a proper or not, or is there any empty modules in the design, or is there any pin which is not defined or not connected. So is there any floating pins are there in the design? So that and all will be taken care. Whatever the RTL code I am be taken care with the check underscore design with a space unresolved. So once everything is fine, then I am moving further with the loading the one more input file, usually called it as a .sbc. So the command used is read underscore sbc. So the read underscore sbc is the command which is used for the to load the sbc file, the predefined command in the which is the architectural level, chip level, you can see, based on the designer specification. Here I have kept the constraint directory. I am loading the constraint directory. Inside that constraint directory, I am calling the constraint underscore top.sbc file. And you should need to be taken care when you are giving this, when you are reading this file, because whenever you are giving this command, it will show the how much whatever the commands you have mentioned in the SBC file, whether it is taken successfully or is there any command which is failed. So at that time, you should need to make sure like any failed command should not be there. All the commands should be successfully read. So then on SBC constraints will be read properly. If it is not reading properly, if it is telling some failed options are there, the failed commands are there in the design. After reading this SBC file, it is giving those. At that time, you need to go back to SBC and try to check with respect to the command which has failed. So until unless fixing those things, you shouldn't need to move further. So if you have some failed commands in the SDC file, if you are moving further, that may create to the issues again, because whatever the command is failed, that is the constraint what you are mentioning, that is not applied there. So that is not, that SDC constraint file will not be completely loaded. So at that time, what are the constraints I have defined that might not be applied to the complete design. So that's where your design will not going to be optimized out completely, or the quality of the gate level netlist you are generating, that might not be meeting your the expectations. So once after that, I'll be moving. Once after setting up with all the three inputs, I'm moving further with the three-stage process, that is a generic, mapping, and optimization. Here, generic is nothing but the translation only, the translation process. So before starting up with the generic mapping and optimization, I have the options in the tool to put the weightage or put the effort level. Usually in the tool based we will call it as a effort level. So if I want to put some effort, I want to try to tell a tool to put a more weightage on my particular stage. It might be a generic, or it might be a mapping, or it might be a optimization stage. So usually we have an effort level with some expect to take a mapping stage. So at the time, what they can do, they can put the effort level to high to the particular mapping station. Effort level means I'm putting a more weightage on that particular stage. I'm telling the tool to take a concern about that particular stage. I'm telling to do so to the tool. So that's where the effort level comes into picture. Here I'm going with the medium because my design is not that much complex. I'm going with the medium. If it again depends on the designer how they are interested to choose with based on the weightages how they want to put the low weightage they want to put, or a low or a high. So it depends it depends on the designer. So currently I'm going with the medium weightage, that is a medium effort level. So the command used is set underscore db sin underscore generic underscore effort level to medium. The same way the same way I am setting the effort level to mapping and the optimization. The command used is set db sin underscore mapping map underscore effort level, that is set at to medium. The same way set underscore db sin underscore set underscore db space sin underscore opt underscore effort level. So I am setting it to medium. So once after the effort level I have added, I have put a weightage on the all the three stages. Then I am moving further with the generic, mapping, and the optimization. As I have already told, the generic means it will try to convert my RTL code into an RTL code into a generic Boolean form. So usually the technology independent, and further we will be moving to the mapping. In the tool will try to bind or to try to map the standard cells available from the library to the design. So this is where the usually a technology dependent, because I am making use of the technology libraries available. So that's where I'll be loading my .lib file. So I'll be the standard cells available from the slow.lib will be mapped to the design in the sim underscore map stage. So once after that, I'll be doing the optimization. The complete design will be optimized based on the targets I'm setting in the predefined constraints. It might be a timing, area, and the power. So the tool will be optimized. The complete design will be optimized based on the targets like the targets like timing, power, area. The predefined constraints I am setting based on the predefined constraints. So making use of the predefined constraints, the tool will try to do the optimization with complete design. So once after that, I'll be writing out my HDL file. So HDL, write underscore HDL, I can able to generate the gate level netlist. So you can make use of a command, write underscore HDL, space, greater than symbol, then space, you can give the file name with the file extension. the file name dot SDC, the counter underscore SDC dot SDC. The file extension will be .stc. Once after that, I have the options to generate the power report, area report, even with the gate count information also. You can just make use of report underscore power for generating the power report, and report underscore gates for generating the gate count information, and even with the timing report, the report underscore timing for the timing report generation, and the same way area report also. Report underscore area will give you the area information. If you want to see all those things in the pictorial representation, you can just make use, or you can enable the command GUI underscore show. So usually GUI underscore show will show you the genus graphical user interface, as you can see from the pictorial representation. This will give you the schematic view of your gate level netlist, whatever the netlist file you are generating backend, so that you'll be able to see the list of all the logical connectivity information from the file. If you want to put it in the schematic view representation or a pictorial representation, you can able to see it from the schematic view. So you can just click on a higher cells and right click and take it to a main window or a new window. Or else you can just go to the plus option available here. You can able to see plus option. If you click on this plus option, you'll be able to see the schematic view. If you click on the schematic view, you can able to see the schematic view of your gate level netlist. So this is all about the synthesis tool. So I'm just moving further again with respect to the reports from the GUI mode. This is the power report, how you can able to see it from the graphical user interface of my design. As you can see, the power report, I'll be going to the power option. If you go to file option, you have a different options like netlist statistics, where it will give you the list of the cells. It might be how many sequential cells are there, how many logical cells, that is nothing but your combinational cells are there, sequential cells are there. Is there any logics like inverters, buffers are there? That information also you can able to see. If you go to file options, from their summary, even with the netlist statistics, all those informations you can able to check it from the file option also. If you want to see the power report, you can go to power option. If you want to see the timing report, you can go to the timing option. From the timing option, you can just open the timing debugger window. So I'll be just taking you, this is a power report where you can able to see the leakage power, internal power, the switching power, and even with the net power. All these informations for a complete design you can able to see. So the same way, timing debugger window, as I have already told, if you go to timing option, you can able to see the timing debugger window. And you will be able to see the category summary. If you go, it will show the total paths. So how many paths are there in the design? So the timing paths, the total 32 timing paths are there, and how many paths are passing and how many paths are failing. Failing is nothing but the path is getting violated. If I am taking, usually for a Genesis synthesis solution tool, by default we will be generating with the setup timing. So again, if you want to like usually if you are by default the tool will generate for the setup. The same thing if you also you can able to check for the hold also. You should need to change the check type. So here the no path is violated, that's why the passing path is total 32 paths. The failing paths are 0 here. And you can able to see the negative worst slack, total worst slack and all. Currently it is not showing here because if you go to path, you can just see here the path list. If you select any one path, you can just enable here and right click and take it to path analyzer option. Then it will show each and every path. What is the slack I'm getting? And actually what are all the things taken care in that particular path. What is the arrival time? What is the required time? All those informations you can able to see in detail. Along with that, is there my check type is BIT or not? That also you will be able to see. So like this we will be checking. As I have already told, area report. So you can see this is all about the area report from the GUI mode. If you are going with the terminal, you will be able to see the report like this. So I'm just moving further the summary. So what and all the things I have done, I'm just listing out once again here. First, I have set it up with the libraries. So once after setting with the library, I'm reading the HDL files and elaborating the design. And after that, I'm checking check underscore design for checking whether whatever the RTL code I'm reading, is there any issues with my RTL code once again. is there any empty modules in the design, or is there any floating pins are there in the design? That is nothing but is there any the pin which is not defined properly? That and all will be checked. Once after is nothing but whatever the constraints I am writing, based on the constraints only, the tool will try to do the optimization, and it will see the timing violations also based on those based on the predefined constraints I am setting. Based on that only, my tool will try to do the generic map. Usually generic means my RTL code will convert into Boolean form, generic form, and then once after that I'll try to map all the generic form to mapping with the standard cells available from the library, and I'll do the optimization. So based on the constraints I have applied. So once after that, I'll be checking for the output files, that is a gate level netlist and STC, and analyzing the reports. So if I'm going with the timing analysis, so whatever the timing constraints I'm getting, so that will be. So here you can see I have just taken one report analysis. Here I have taken timing analysis. So whether my timing is met or not. So if I am getting zero timing part violations, then with respect to setup and hold, here in the usually what are the timing reports we are checking after the synthesis, it is a pre-layer static timing analysis. Usually you will call it as a pre-layer static timing analysis. Now actually we can say only the ideal clock signal will be considered. So that's why I'll be very only with respect to the setup violations. If I'm getting any hold violations also, I'll be ignoring here, because my clock is not yet propagated. So the actual clock propagation has been not taken place. So the whatever the timing, if I'm getting any violations in the pre-layer static timing analysis, how I can fix those violations? There are two ways. One with optimizing your the constraints, predefined constraints I'm giving, by tightening that, or by modifying the constraints, predefined constraints I have. So one more, the another way, I should need to do the incremental optimization. By doing the incremental optimization, but what happens in the incremental optimization is your area get increased, but you can able to fix the timing violations. So the two cases will be used for fixing the timing violations. As you can see, if the timing is met, I am moving further. I am generating the report further. If the timing is not met, again I am coming back to the constraint file and tightening my constraint file, and I am doing once again the synthesis process for the incremental optimization, and I will be trying for the incremental optimization and trying to fix the timing violations. So once after this, I'll be taking the gate level netlist and the SDC file generated further to the Innovus tool. So till these parts, the synthesis process completes, making with a help with a using Genesis synthesis solution tool. So from the cadence, the Genesis synthesis solution tool will be used for the synthesis process. So participants, is there any doubts till this point? So I'll be just next I'll be moving further with the physical design part. So if you have any queries related to synthesis, you can just unmute and you can discuss.
Some of the questions are there in chat box. So the first question is, which algorithm is used for binding and mapping?
See, binding backend tool is calling. So all those are actually the script written. If you go back in the tool backend, you can able to see. Usually that and all information will not be given, but I can say the mapping is a command which will helps me to map whatever the standard cells available from the library. So here I am taking here I just have a tool. So I am just making use of the commands what and all available. So backend directly what algorithm it has been used, it will not be given here, but you can just give us some time. I will try to check it backend, because the again tool it is taken from the cadence. I should need to see backend, because we have only the options to see the mapping, generic and optimization. And actually backend what the tool is doing in the mapping stage and the optimization stage, and even with the generic stage. So any further queries? Usually in the mapping means it will try to bind what and all the standard cells are there. All those standard cells will be mapped in the mapped to the design. So whatever the generic expression I have, after the sim generic option or after the sim generic stage. So the tool will try to make use of the standard cells available from the library and try to map those standard cells to the design.
Madam, what is incremental optimization?
See, incremental optimization means, for example, after the synthesis stage, I got the violations. Usually we will call it as a pre-layer static timing analysis. If I am going further with the STA after the synthesis stage, I am checking for the timing report. So when see, I have a set of violations after the synthesis stage. So how I can fix those violations with respect to setup timing? So at that time, I'll be going with the two cases. One with the tightening my constraints, whatever the timing constraints, whatever the constraints I have written in the SDC file. So I'll be tightening. I'll be trying to modify the constraints I have written. One case, another one is the incremental optimization. Incremental optimization means the tool will try to take out the constraints file defined and wherever the path, whichever the path is violating, the tool will try to add some cells, add some buffer cells into that particular path, and it will try to avoid the timing issues. So that's where the incremental optimization comes. I'm telling the tool to fix my timing violations by incremental. So incremental optimization. So usually optimization means the tool will try to add some cells into that particular path. Which path? Usually whichever path I'm relating with so and so slack. So obviously the slack will going to be negative. I should need to make that slack to positive. So you can, so usually no need to bother about, even if I have a high slack also not a problem, but it should need to be positive. If it is negative, then only the tool will say that path is violated. So that's why whatever the path is violating, the tool will try to add some cells into that particular path and try to fix the timing issues. So delay will be included and will again optimizes your timing issues. So that's where the incremental optimization comes into picture. So any queries?
Ma'am, one more question. So from the
Yeah.
gate count report, is it
Yeah.
possible to find the physical area?
No. See, gate count means it will just gives you the how many gates are, how many the cells are used, how many instances are used in your design. That count information you can able to get. But logical information, as I have already told, the complete logical information for each and every cell, each and every cell. Can you please mute from your end? Yeah. So each and every cell, the complete physical information we can able to get it from the .left files available from the foundry. If for example, if I am taking any one technology, it might be a 45 or a 90. You can just go back to the left directory. The file you can able to see .left files. If you go to .left files, you can able to see the complete physical information about the abstract view of your each and every cells available in the design. So currently you can't able to see the logical information from the gate counts. You can just list out how many counts, how many gates are there in the design. That and all will be listed with the gate count command. So any further queries?
Ma'am, what is path histogram?
Sorry?
What is path histogram?
Path histogram. See, one option, if you go to timing debugger window, we have the options to see the timing path. What are the timing report I am generating? For that timing report, I have the option to see the histogram. Usually how we will be seeing. So the same way, we have the option to see the histogram in the timing debugger window. But actually timing the path histogram I am not familiar, but histogram we can the timing paths, whatever the timing paths are there in the design, that each and every path we can able to see the histogram, the pictorial representation or the graphical or you can say the graphical representation of my each and every path. That you can able to see from the timing debugger window.
Ma'am, one more question is there.
Yeah.
How to convert one technology file area into another technology file?
See, technology file, as I have already told in the script. So I am just coming back to the script. See here, the whatever the path I am setting, you can just change the path. For example, before I have set up with the 90, then you can just make it as a 45. So currently I am interested to run the design with the different technology node. At that time, you can just change the library search path I am giving. No, what are the directory I am setting, the path for that particular library directory. At that time, you can just go to that the technology node, whichever the technology node. It might be 45 or it might be 90. Based on that, you can just set. So once after setting with that, it will be taking whatever the area report or power report or even you are checking with the timing. All these things will be generated based on the library you are making use. So whatever the library you are making use, from that particular library, you'll be able to see all these reports. So area information, power information, all these things will be taken from the technology node which I am making use.
Ma'am,
So
how to compare the area, power, and delay of two different technologies?
see, technology is nothing but you can able to see the timing information. As I have already told, three cases we have. One is so when I am going with the technology libraries, we can able to see with the three cases. One is slow dot lib, fast dot lib, and the typical dot lib. So as in the starting session itself I have mentioned, slow dot lib, fast dot lib, and the typical dot lib. These are the dot lib files or the technology libraries available. With respect to worst delay I am considering. So at that time I will be going with the worst timing or worst delays I am considering. I will be going with the slow dot lib, where the slow dot lib comes into picture. And if I am going with the minimum delay and best case, so I am going with the best case, then the delay will be minimum. So that's why I am going with the fast dot lib. If I am going with the moderate, that is nothing but usually typical dot lib. So I am going with the moderate conditions, then I will be going with the typical dot lib. So these are the three cases. You can make use of these libraries and you can just see the report. What I can say is, actually for simple designs you might not be able to see that much difference in the report. If you are going for the complex designs and all, at that time obviously you will be able to see the difference with each and every report you are generating. For the complex designs you can able to see, because these are whatever the simple design if you are taking, at that time it will be there, difference will be there, but it will be a slightly difference you can able to see, not that much. Only for the complex designs and all you'll be able to see the difference with the simple designs.
Ma'am, why always we use slow dot lib?
It is not like I have just shown. Worst case, usually I am considering the delays with the maximum. So it is not like most of the time. It again depends on the designer. If the designer is interested to go with the worst cases, I want to check my timings, everything, or even with the area reports and all with the worst case, then they can go with the worst case. If they are interested to go with the minimum delay for the best cases, then they can go with the fast dot lib. It is not like only the slow dot lib is used. All the three you can make use. Only the thing is, if the designer is interested to do with the worst case, so I should need to check my design, or I should need to synthesize my design for the worst case. Then they will be going with the slow dot lib. Worst case is nothing but I will be considering the maximum delay values. If you go back to the library, you can able to see all those informations and all. So am I answered your query?
Yeah, yes, ma'am. That's all. Thank you, ma'am.
Oh, yeah. Shall I start up with the physical design process?
Yes, ma'am.
Because again, we have a physical design process with the five stages. So let us see one by one in detail.
Okay.
So now start up with the physical design process. Usually, what actually the physical design process means? So it is a process where I am transferring the circuit description. As you can see, the logical gate level netlist I have generated from the synthesis. That is just usually, as you can see, the gate level netlist means it completely includes the logical information, or you can say the circuit description. So that circuit, the process of transforming my circuit descriptions into a physical layout. So the physical layout in, or another way you can say, usually which describes the position of my cells and the routes for the interconnection between them. What are the routes and like usually what are all the nets I'm routing, or you can also say whenever I am telling routing means usually the interconnection between one cell to the another cell, from one net to another net, you can say. So all these descriptions will be given in the layout form. So usually we will call it as a physical design process. So the physical design process is nothing but transforming of my circuit description into a physical format or a physical layout form, or you can say the translation of my gate level netlist into a GDS form. Usually call it as a physical design process. So as you can see, the gate level netlist, I'm converting it into a GDS form, or you can say layout form. During the physical design process, usually all these design components are instantiated with their geometrical representations. Usually in the physical design stage, what happens? All the design components are instantiated. Whatever the design, the design components I have mentioned in the netlist, that will be instantiated with their geometrical representation. It might be a macros, or it might be a cell, or it might be a gate. So this is all about the physical design process. I am giving the input as a netlist and generating the GDS file. So coming back to the next stage, as you can see, the physical design flow. So it is a back end of the ASIC flow, usually called as a physical design flow. So the physical design implementation. So when I am telling physical design implementation, so usually it is also called it is also one of the stage in the ASIC design flow. So usually it is also known as a place and route stage. So the place and route stage. So usually the physical design flow is also called, physical design process is also called as a place and route stage. And also the tool used for the physical design process is Innova's from the Cadence tool. From the Cadence, the Innova's solution tool will be used. So now let us start off with the physical design flow. Usually it includes again the 5 stages, or it's a 5-stage process. One with the floor planning, power planning, placement, clock tree synthesis, and the routing. So these are the 5 stages included in the physical design flow. So I'm just moving further. As you can see here, the inputs required for the physical design process based on inputs, as you can see, the gate level netlist and the STC constraints. So the gate level netlist is generated from the synthesis tool, and the STC constraints generated from the synthesis tool. Usually this is a block level STC. I'll just show you the picture and representation of your block level STC afterwards. So once after, along with the gate level netlist and SDC, I'll be considering two more input files, that is a library, and the 2 more inputs I have taken. One additional input, as I have already told, .lib and the .lib. So the timing library, that is a .lib, and a physical library, that is a .lib. So physical information I am making use. So that's why I am making use of .lib file. So the physical library, the library exchange format. So these are the 2 inputs, the additional inputs along with the gate level netlist and the SDC constraints. So the primary inputs I am taking to the so the physical design flow is gate level netlist, constraints file, and the technology libraries. In the technology libraries, I will be using timing library and the physical library. When I am telling the timing library, the file extension will be .lib. When I am telling the physical library, the file extension will be .lib. So the .lib stands for library exchange format. The .lib stands for liberty file format. So once after giving with these things, I will be generating the reports with respect to power, timing, area, and along will be generating the GDS file. So usually the reports will be generated from the placement onwards. From the placement onwards, you will be checking the power report, timing report, area reports with respect to placement stage, clock tree synthesis stage, and the routing stage. For each and every stage, you can able to see with respect to power, performance, and the area. These three targets, with respect to these three targets, you can able to see the reports. And along with this, if any congestion reports are there, so that also you can able to see. I am just listing out the same information that is for the timing library. So as I have already told, it includes the complete functional information about the cell. For each and every cell, what is the port information, cell type, operating conditions, power consumptions, or even the timing information used. All these information from the dot lib. So the same way pictorial representation, as you can see the same example I have taken here. So I'm just moving further with the physical library. So as I have already told, the physical library is nothing but, so usually it will be the complete, the abstract view, the the abstract view of my each and every cell in. So that information we can get it from the physical library. When I am telling abstract view, so abstract view, actually what the abstract view includes means, or it contains means, so usually the cell name, or it might be a size of the cell, allowable orientation, or even with the pin information, or the layout geometries required for that particular cell, that information, or if I am going with the routing, then what are the routing blockages I am making use, or the pin or a power pins I am making use, that information and all will be able to get it from the physical dot library. Along with that, you can able to see the process antenna area information. All these informations will be given in the .left file, usually called as a physical library. The file extension is .left, where .left stands for library exchange format. So I am just taken one example here. You can see here the abstract view. So here you can able to see the NAND gate. For the NAND gate, what actually the abstract view means, the dimensions of the, and also one more thing, in the left file, we will be able to see whatever the core area, so the boundaries, whatever the boundary information, that also you can able to get it from the, you can able to get the boundary information and all, you will be able to get it from the .left file only. So whatever the PR boundary you are setting, that information you can able to get it from the physical library also. So the same way I have given whatever the metal information for the routing, whatever the metals I am taking, that metal information will be given in the physical .left file. And you might be asking what actually the metal ranges and all. Again, the metal ranges vary with respect to the technology node. For example, for 90, I am taking the metal range from metal 9 to metal 1 to metal 9. The same way for 45 nanometer technology. Like the based on the technology node, the metal layer information, the metal layer range may varies. So all these informations you can able to get it from the physical library. So I'm just taking the sample of a physical library. As you can see here, the complete abstract view information. And along with that, the metal layer information, the metal 1. For that metal 1, what is the width, what is the spacing, and what type of a routing it is used, and whether it is a horizontal direction. I am using a horizontal metal or a vertical metal. Like how the direction I am making use of that particular metal. That all types about the logical connectivity of my all the gates, or you can also say the standard cells or the macros included in the design. That logical connectivity information you can able to get it from the gate level netlist. Along with that, usually the output of the synthesis is taken as an input to the physical design process. Whatever the gate level netlist I have generated from the synthesis, that is taken as an input here. So usually the netlist contains the information about the standard cell instance, the standard cell instance name information, or even with the name and the drive strengths, what are the drive strengths I am making use that information, and even with the macros and the memories are there in my design. For those macros and memories, all the instance that information and the port of what are the ports, the port information about each and every cells in the design. That we can able to see. Or you can also set the interconnector details or the interconnected information about each and every cell included in the design. That logic information you can from the gate level netlist. You can able to see here the next information, interconnect information in the detailed interconnect information, and even the instance names also, port names also, even drive strength information. All these things you can able to get it. And coming to one more input, that is SDC. So you can able to see here this is the SDC, which is a block level SDC, which is generated from the synthesis tool by using the command write underscore SDC. So the write underscore SDC is the command I am making use. I am generating the SDC file. Usually the generated SDC file is the block level SDC, which is I am taking as an input in the physical design stage. Once after I have loaded all the inputs, next I should need to check. Usually, in the first session itself, one participant were asking what actually the sanity checks and why we were going before the floor planning. So to answer that query, you can see here. Usually, there in the synthesis stage, we will be going. Usually, what are the checks we were doing? We will call it as a linting checks. When it comes to physical design process, we will be calling as a usually we will call it as a sanity checks. So what actually we are doing in the sanity checks means we will be checking the quality of the inputs and loading to the design. So what are the inputs I told? All the three inputs. So the quality of all the three inputs I am making use for the physical design process. That will be checked here. If I am taking only the netlist, the quality of my netlist, how the quality of my netlist will be checked with a sanity check. The quality of the libraries I am making use, the quality of the STC file I am making use, that will be checked in the before the floor planning stage. So this is all comes under the sanity checks. So it will also consist of the checking the issues related to any timing libraries or physical libraries or constraints or even with the whatever pins IO pins I am assigning, that and all. So as you can see, the library checks. Here it will be checking all the cells included in the .lib. Timing libraries. The timing library means .lib. Physical library means .lib. All these things will be checked. The same way, netlist. Netlist means it might be a floating pin information, or is there any undriven IO ports are there or unloaded IO ports are there. That, and even if any multiple drivers are used in the design, all those things will be checked with the gate level netlist. Is there any floating pins are there? If any floating pins are there, and I am directly loading that gate level netlist, I might not be getting a proper quality of my result. So that's why these things will be checked, and you should need to see whenever I am making use of checking with a netlist, it will show is there any errors with respect to if it is any I use, it will show if any errors are there with that whenever you are checking, then you shouldn't need to go directly to the floor planning. You should need to come back to the synthesis once again and cross-check the netlist you have generated with respect to the error you are getting. So the same way with the constraints file, even with the timing library. Usually timing library, usually the technical library I'm using, it might be a timing or a physical library. So again, you should need to come back to the founder and you should need to cross-check if any errors are there in the libraries, because usually we don't have any options for editing the libraries, because whatever the libraries we got, that is from the foundry. It is usually we will be getting from the library vendor. We don't have any options to edit these things. So this is all about the sanity checks. Usually we will be checking the quality of my inputs loaded into the design, whether it is proper or not. Properly loaded all the input designs. Is there any errors with what are the inputs I am loading? That will be checked in the sanity checks. So once after the completion with the sanity check, and after the sanity check, I am proceeding further with the before the floor planning. I have one more thing. For example, previously I have done with the 45 nanometer technology. Now I am moving further with the 90 nanometer technology. At that time, what happens? The tool directly it will take the 45 nanometer, because previously I have done with the 45 nanometer. The the default technology node it will take, the tool, if you are starting with physical design process. So to avoid that, the users can make use of the command for setting the node, the technology node. You can just, if I am generating any reports and on backend, it will call the default technology node. The tool will call default technology node. Default technology node means previously, like for example, yesterday I have run some the design with a 45 nanometer technology node. Today I am trying with the 90 nanometer technology node. Then if I am not setting any technology node, directly the tool will call for the 45. To avoid that, you can just set up technology node by using the command set design space hyphen process with the technology node. You can just mention, if it is 45, you can mention 45. So no need to mention nanometer. Directly you can mention the number. So set design space hyphen process space the technology node you are using. 90, 45, like that you can just mention. Once after that, you can start up with the floor planning. This one thing should need to be taken care, because whenever you are checking any reports and all, at that time the node, the design, the technology node will be whatever you are setting, that one only will be there. If you are setting the previous one, the default, whichever the technology node you have run, the different technology node means it will show the default one. So to avoid that, you can just go with that. So once after this, after I am starting up with the floor planning, so usually in the floor planning, what and all the things I am checking. When I am telling floor planning, usually what and all the things I am checking. The floor plan means usually it is a process of chip area or into the core area. So usually, usually you can say establishing of my die size of the design. Usually, you can also say the process of estimating the layout of my design. Sorry for the inconvenience. I'm just continuing further. To start off with the floor plan, as I have already told, floor planning is nothing but I'm placing all the macros into the core area. Usually, what happens in the floor plan stage means usually it is a process. Usually it is a process where I am estimating the layout of my design. So that is nothing but I am estimating of my die size. Usually estimating of my die size of the design. That will be taken care in the floor planning stage. So along with that, it also includes the creating placement standard cell rows. The placement rows of standard cells will be created in the floor planning stage only. As you can see, if you are going with the placement stage, the rows will be there. Inside that rows only standard cells will come and sit there. So that rows will be created in the floor planning stage only. With that, IO placement. Usually, usually determining the die size. Usually call it as the estimation of my die size. And along with that, I am checking or I am creating usually it is taking care of the creation of those standard cell rows and pin assign. What are the pins I am assigning? All these things. You can also say the IO pin placements. That will be taken care in the floor planning stage. And along with that, if I am listing out some goals with respect to the floor planning, what are the goals? So to get a better or a good floor planning. So these are the some constraints I should need to meet. So usually, to get a good floor plan, I should need to minimize my total chip area usage, and along with that, even and also I should need to minimize the routing congestions in the design, and even by arranging, or you can also say the proper arrangement of my blocks in the chip. So by arranging properly all the macro blocks in the design, that will be by arranging all the proper arrangement of the block will also gives you the good floor planning. Even it will by deciding the IO pads location. You can say the IO pins or pads and placing that location, deciding those things also, I can be based on those things also I can get a good floor planning. So as I have already told, these are the few goals. So now let us check for the two, as you can say, the floor planning control parameters. I can say now you can see the floor planning control parameters. So usually I am considering two floor planning control parameters like aspect ratio and the core utilization. So aspect ratio and the aspect ratio and core utilization will be called as the floor planning control parameter. So what actually the aspect ratio and what we will do in the aspect ratio, like in the floor planning by setting with the aspect ratio. As you can see, aspect ratio is nothing but it is the ratio between the horizontal routing resources and making use to the vertical routing resources. It is the ratio of between the horizontal routing resources. You can say here horizontal routing resources between the vertical routing resources. So you can also say it as a aspect ratio is equal to W by H, where W is the width of my core area and height of my core area. H is nothing but height of my core area. So W by H. So we'll gives you the aspect ratio. Usually, it also determines whether you get a like for example the shape of the core, or you can say the core area or a die what you are setting. So the chip area, that the shape of the core area will be decided on the based on the aspect ratio I'm setting. As you can see, if the again it depends on the designer. Based on the design specifications, they can change the aspect ratio. If I'm setting equal to 1, it will going to be the shape of my core area will going to be the shape of my core will going to be a square shape. So if I'm setting greater than 1, it will going to be a vertical rectangular shape. And if I'm setting less than 1, it will going to be a horizontal rectangular shape. So it again depends on the designer. The macro shapes and all comes into picture. How based on their macros, the macro sizes and all, they can make use or they can choose these aspect ratios. So once again, this is a designer specification. So usually aspect ratio is nothing but it is the ratio between the horizontal routing resources to the vertical routing resources. If I am setting the aspect ratio is equal to 1, my core area, the core area shape will going to be a square shape. If it is greater than 1, it will going to be a vertical rectangular shape. If it is less than 1, it will going to be a horizontal rectangular shape. So this is all about the aspect ratio. So aspect ratio is also one of the floor plan control parameters. So next moving to the core utilization, and this is also one of the floor plan control parameter. Usually in the core utilization, what actually we will do? So in the core utilization, as you can see, usually it refers to the percentage of my core has been occupied. Usually the core area occupied by my standard cells or macros, and even if I'm using the blockages in the design. So all these comes into picture. So usually it refers to the percentage of the core area occupied or core area utilized by the my design, or you can say the standard cells or macros or blockages in the design. So usually call it as a core utilization. So for this case, guidance tool. So we will be starting up with a core utilization with a 40%. Usually, why we were going with the 40% means starting we will be initializing with the 40% means in the later stage we will be adding the standard cells in the placement stage or distribution of clock signal in the clock tree synthesis stage. They are also building their incomes. Again, we will be adding some cells and even going with the routing. We need a more again. We need a more space at that time. So to avoid any issues in the later cases, we will be starting up with the 40%. So 40% is nothing but 0.4. So we'll be setting the aspect ratio again 1. If I set it will go into the square shape. If it is less than 1, it will go into the horizontal rectangular. It is greater than 1, it will go into the vertical rectangular shape. So the same way core utilization I'll be giving with the starting initial. I'll be going with the 40%. Why I am going with the 40% means the remaining percent. So the remaining percent will be utilized in the later stages. So if at the time if you are facing any issues with respect to the spacing, so again I should need to come back. To avoid that, I am just going with the starting initialization with the 40%. So this is all about the floor planning. So I have listed here some guidelines. Usually, what are the guidelines need to be taken care in the placement stage? So first thing, I'll be dragging all the macros into the core area, and once after that, I'll be checking. Usually all the macros should be placed in the all the macros should be placed at the boundary, whatever the PR boundary I'm creating, so the nearer to the PR boundary. So I will be placing all the macros to the boundaries, and I should need to check once after the placing. So whether macro to macro communication is there, or is there any macro to standard cell or a macros to pin communication is there. That should need to be taken care. If it is macro to macro communication, then all the macro to macro communication is not there, then that macro I can abort. Usually abort is nothing but I'm not giving any spacing between those macros because it is not communicating. Means that there is no pins for connecting to one macro to another. Whenever I am telling communication means the pin connections comes into picture, or the routing comes into picture from one pin to another pin, or one net to another net. So this is all about the macro guidelines. Along with this, and I should need to take care whatever the lower left corner of my macro that should need to be placed on the grids. The lower left corner of the macro should be placed on the placement grid. Usually that will be back-end display. You should need to enable the grid option from the all color window in the graphical user interface of your Innoverse tool. You can just enable the grid option. You can able to see the grid. Based on the grids, lower left corner of your grid, you can just the lower left corner of your macros, you can just place on the particular grid. So once after that, and even if and also you should be and also if any macro to usually macro to any standard communication or macro to macro communication is there, then you should need to give us some spacing, because again when I am doing routing or even with the placement stage, the standard cells were coming and sitting. If any communication is there, again the routing and all will be taking place. To avoid that, I will be placing the I am giving the spacing for the pin connection. Once after that, if around to avoid any congestion issues, I should need to add blockages or halos around the macros. What are the macros I am making use? Around the macros, you can put a halos or a blockages. Usually, that will avoid any cells to discussing those things in the later. So usually. This is all about the guidelines that should need to be followed while placing the macros. So to get a good floor planning, you should need to take care of all these things. And one more first, to check as I have already told, one macro to another macro, is there any communication? That will be checked with the help of fly lines. So usually we can say the virtual connection. As I'll just moving further. So here I'm just moving further with the power planning. So the next stage is the power planning. So in the power planning, as I have already told, the power will be distributed. The power will be the power distribution will be taken care. Usually, the power planning stage, we were distributing the power to the all the blocks or all the modules in the design. So it might be a standard cells or macros or any other cells. So that the power distribution will be taken care here. Usually the power distribution network will be usually the power grid networks. Usually you can call it as a power grid networks will be created to distribute the power equally to the throughout the design. So usually the power will be distributed throughout the design by creating the power grid network. By creating the power grid network, we will be distributing the power. And along with that, usually power nets and ground nets are created around the core boundary with a higher metal layers. Usually, usually to distribute the power, we will be making use of a power nets and the ground nets. And also, we were using the higher metal layers here. So why we are going with the higher metal layers means usually higher the metal layers, the resistivity will be less. So that's why we were preferring with the higher metal layers here. And whatever the power distribution it is there, that is usually a mesh kind of a structure. The power planning usually will be done with a mesh kind of a structure. So we were creating a mesh kind of a structure to distribute the power around the complete design. So there are at least 3 levels of power distribution will be taken care in the power planning. One is with the rings, stripes, rails. So rings means it will be carries the VDD and the VSS power nets from usually around the chip. So usually it distribute the power around the chip. I'll just show you the pictorial representation. The next is the stripes. Usually the stripes will carry the power distribution will be taken around the chip. Once after that, from the rings to the chip, the power will be carried from around the chip. Along with that, from the rings to the chip around the core area. So usually the power stripes are created in the core area to take the power from core rings to the core area. When it comes to rails, usually the VDD VSS nets will be the VDD VSS power nets will be used to connect the VDD VSS nets of the standard cells. So usually the standard cells rails will be created to distribute the power to or power stripes to the standard cells of my power and ground pins. The power and ground pins of my standard cells will be connected with the standard cell rails of my power and ground nets. So usually the railing standard cell rail creation, we will be going with the lower metal layers. As you can see here, the ring creation. So as you can see around the chip, around the core area, I am creating power rings. Usually the power rings, the creation of power rings again, I will be going with the higher metal layers. Metal, for example, if I am going with the 90 nanometer technology, the range will be 1 to 9. So I am just taking metal 9 and metal 8. Metal 9 for a horizontal and metal 9 for a horizontal and metal 8 for a vertical. So this is all about the ring creation. So I am just moving further with the power plan with the stripes creation. As you can see, from the ring to the around the core area. So around the core area, I am creating a number of stripes, vertical stripes and the horizontal stripes to distribute the power. To distribute the power around the core area from the rings. So from the rings. So where I am making use of stripes, usually vertical stripes and the horizontal stripes. Here also, as I have already told, the higher metal layers will be used. So coming to the standard cell rail creation. So as I have already told, whatever the standard cell rails, whatever the standard cells are coming and sitting here, for each and every standard cells, we have a VDD and VSS pins. Any queries? Okay, I'll be moving further. I'm just moving further with the next stage, that is a placement stage. Before going with the placement stage, I'm adding some physical cells So usually the physical cells, why I am adding these physical cells before the placement? So usually when I am starting up with the placement stage, there might be a chances of placing my standard cells outside my core area. So to avoid that, if it is placing outside the core area, I am losing my data, or I am losing my design from whatever the standard cells which are placing outside. So to avoid that, I am giving a barrier to the design, or you can say the core area. To the usually you can say here in the pictorial representation, I am giving a barrier to the code. So usually pre-cap and the post-cap. Starting also I am giving, and at the end also I am giving. I am giving a barrier to the core area, so that whenever I am doing the placement, all the standard cells will be placed within the core area. It will not be moving outside the core area. To avoid this kind of issues in the design, so we were going with the end cap cells. Usually end cap cells will be used to avoid any missing of my standard cells or missing of my designs to coming out of my core area. To avoid that, I am using it as a barrier to the core area. So usually pre-cap and the post-cap. Pre-cap means I will be using the starting. Post-cap means I will be using it at the end. The left corner and the right corner. You will be seeing these cells added into the design. So these are the things I will be adding into the design. So usually handicap cells will be added to avoid or to provide a barrier to the design. I am going with the handicap cells. If I am going with the well-tap cells, so as I have already told, so usually well-tap cells will be added to avoid any latch-up issues are there in the design. As you can see, I am using all the standard cells. So for each, as you can see, if I am checking backend, so there might be a chances of getting any latch-up issues in the design. To avoid that issues, I'll be just adding the well-tap cells. Usually when I'm telling handicap and the well-tap cells, I'll be making use of the filler cells. Again, the size may vary with cell to cell. Fill 1, like you fill 2, fill 16, like that. The list will be there. Higher the width, like higher the cell, higher width will be more. So you should need to choose the lower cells to avoid any issues with respect to the DRC, or even the area is higher the cells, the area will be more. The area consumption will be more. So at that time, you should need to take care of the lower cells, so that you will not be having any spacing issues, and even with the DRCs. So here, like a fill 2, fill 4, you can refer, or even with the fill 1 also, you can refer for adding the end cap and well tap cells. So this is all about the physical cells which are added before the placement stage. So I am just moving further with the placement stage. So when I am telling the placement, the name itself says placing. So actually, I am trying to place all the standard cells into the design. So placement means I am trying to add all the standard cells into the design. So I am just moving, as you can see from the pictorial representation. So I am trying to place all the standard cells into the core area. And that you can able to see all the standard cells will be placed inside the standard cell rows which are created in the floor planning stage. Whatever the rows you can able to see, these rows usually call it as standard cell rows. These standard cell rows will be created in the floor planning stage only. So all these rows will be standard cell rows will be created in the floor planning stage. But in the placement stage, all the standard cells will come and sit on the standard cell. Can say what usually you can say minimizing my layout. By minimizing the layout, I can get a better placement data. So the same way, by minimizing the length of my critical nets, by reducing the length of my critical nets, I can reduce the critical net delay. By reducing the critical net delay, I can get a good placement database. The same way, even if I am considering the power dissipation, if minimum power dissipation, then whatever the database I am getting, that is a better placement database. If I have any issues with the placement database, if I'm moving further with the routing, I might not be able to route properly. So to avoid that, I should need to have a better placement. So usually routing again depends on how well congested my design, how well I have congested my design. So usually, so that's where here the congestion comes into picture. In the placement stage itself, I am just checking for the congestion. So usually placement congestion is nothing but, so placement congestion is nothing but I'll be checking usually the number of routing tracks available are lesser than the number of routing tracks and required for the design. Usually the routing usually congestion means it is if the number of routing tracks available where are lesser than the number of routing tracks required. Usually call it as a congestion. So usually congestion need to be analyzed in the placement stage after the placement stage. Why means again the routing depends on how well my congested how well the congested my design is. So that's why I should need to take care of the congestions. So usually congestion means it is nothing but number of routing tracks available are lesser than the number of routing tracks required. So that is nothing but congestion. So usually the reason for a congestion means, so one is the placing standard cells near to the macros. What are the standard cells so what are the standard cells I'm placing that is sitting nearer to the macro. So at that time what happens, if macro to macro communication is there should need to be some spacing. So if it is not the case, there in that particular region when I am doing the routing, so net routing and all will be taking at the time the placing, the congestion will be occurring at that particular stage or at that particular region. So usually that may leads to the placing of my standard cells nearer to the macro also leads to a congestion. Even if I did a bad floor planning, so if my floor planning is not good, at the time it may also leads to the congestion. And even with the you can say the number of cells placed in the small area. In the small area, so many number of standard cells are placing. So that also leads to the congestion. That is nothing but if my lots of standard cells were placed in the in that particular region, so many standard cells were placing. So at that time, that may leads to the congestion again. So to avoid the congestion, what and all the things I should need to take care. So one way by modifying my floor plan. So how I can modify? By moving the macros, by changing the core area or a shape of my core area with the setting the aspect ratio. So by modifying all those things, I can get I can minimize the congestion. Usually the placement congestion can be minimized. And I am just moving, as you can see here. Yeah, so as you can see here, the placement. What and all the things I should need to take care. So first one is modifying my floor plan. That is nothing but moving macros or any changes in the core area or a shape of my core area. So one way, another one way is spreading of my all the cells. Wherever the overlapping of cells are there, that region I can spread all the cells. By spreading all the cells, I will able to optimize the congestion. That is nothing but I can able to minimize the congestion. So even by modifying my physical constraints, as I have already told, by modifying my or by tightening my physical constraints I am giving to the design, that also will helps me to avoid the congestion. And even the proper blockages around the macros. If I am placing the blockages around the macros, that will also reduces the congestion. So these are the regions. These are the techniques, or you can just take a method where I can reduce my placement congestion. So the placement, usually the congestion is nothing but the number of routing tracks available are lesser than the number of routing tracks required. So usually the congestion need to be analyzed. The placement congestion need to be analyzed after the placement stage, because again the routing results depends on how well the design is congested. Based on that only the routing data, the routing will be the routing results will be checked. So to avoid that any further issues, I should need to be taken care all these things here. Once after that, in the placement stage, so from the placement stage onwards, I have the options to check the report with respect to the setup violations in the placement stage. So if I have any violations with respect to code, I am ignoring, as I have already told you, we were not used any clock, the actual or a propagated clock signal. So I am using the ideal clock signal, so I am just worried with respect to the setup violations, because again the data path will be comes into picture with respect to setup. If I am going with the hold, the clock path comes into picture. So that's why whenever I am doing in the placement stage, if I get any violations with respect to setup, I should need to fix those violations. So once after, if I get any violations, how I can fix? The way is optimization. Usually we will call it as a placement optimization. So by using the optimization option from the green menu, or you can just go, you can just make use of the optodesign -pre-cts command. So it will help you to optimize your, or else it will help you to fix your timing violations with respect to set. So the setup violations will be fixed by optimizing the placement database. So when I am doing the optimization, the tool will try to add some cells into that particular violated timing paths, and it will try to fix the violations. So these things will be taken care in the placement stage itself. Once after the optimization, if you have if any violations are there, you just cross check once again. No violations, you can further move with the pre-synthesis. So the timings, the timings, you can say the setup check timing reports will be taken care. Any setup violations are there, that will be fixed in the placement stage itself. After optimizations also, still I am getting some violations. Then no need to worry. Each and every stage we will be checking the timing, and we will be checking the timing reports. You can move further with the next stage. At the end, the routing stage, we will be checking both the setup and hold violations. So that time I should need to fix with respect to setup and hold both. So coming to the next stage, clock tree synthesis stage. Before start up with the clock tree synthesis stage, is there any queries based on the placement? The placement stage. The till now I have covered with the three stages. First one is a floor planning stage. The next one is a power planning stage, and the placement stage. In the floor planning, I have discussed about the macro guidelines of macro placement, along with the two control floor plan control parameters like aspect ratio and core utilization. In the power planning, the levels of power distribution, we have discussed about the placing of my standard cell, and along with that, so whatever the congestion input I am checking, and even with the timings. Even if you want to see the power reports, area reports, you can able to see after the placement stage onwards. Before the placement, I'll be adding some physical cells. Usually that is a end cap cells to give a barrier to the core area, and a well tap cells to avoid any latch-up issues in the design. So till this point, is there any queries before start off with the clock tree synthesis?
Ma'am?
Yeah.
Ma'am, some of the questions are there in the chat box. So the first question is, GDS2 and Open Artwork System integrated interchange standard are one and the same or different?
See, GDS file is again a binary file format. It is a machine readable format. So that will be taken further for the fabrication. When we were sending a chip to fabricate, then we were taking the GDS file. That is a machine readable file. Whatever the layout they have then that will be written in a machine. That will be written in a machine language. So that will be further taken for the fabrication process. When it comes to open access database, when it comes into picture means if I have any designs, like for example, you can say the mixed signal. I have some designs with analog database and I have some blocks with a digital. So at that time, I'm making use of that open database option. If I'm going with a mixed signal and all, that's where it comes into picture. Even with analog, you can able to see the open database options. The same way, there also what are the libraries you are using, making use of the setting, all those things comes into picture. The same way, database because it is not a human readable format, so a human readable file, so it will be directly read from the machine, then we will send it for the fabrication. So open database means I'll be generating usually from the in-house tool, we will be able to generate the database in the format in the file extension .enc. So the same way, you can able to generate the open database also. So usually that option comes into picture when I am going with the mixed signal. For example, I have some analog blocks in the design and then I am going with the digital part also. Both I am combining and making use at the time that open database comes into picture. So any queries further or shall I move further?
Ma'am, approximately what is the additional power we can expect from synthesis to physical design?
Approximately like what expectations you are getting, like see usually whatever the power optimization, see power means again I'm adding in the placement stage again I'm adding the standard cells and a power distribution whatever the cells are there again the power distribution is I'm doing it might be taking based on the standard cells. So whatever the report I am checking in the synthesis and after the synthesis in the physical design stage. In the physical design stage, I am adding some standard cells into the design. I am checking the power report. Again, I am doing further with the clock tree synthesis. There again, I am adding some cell. Again, I am adding some cells for building and balancing of my clock tree. So at the time, again some cells are added into the design. Then again, the power consumption will be there. So like I can't say the like a percentage in terms of percentage, but it depends on the how complex your design is. If it is not that much complex, the power variation will not be that much. If it is a complex design, then you might be having a more cells into the design. So obviously, the power consumption will going to be usually the power consumption will going to show the difference with whatever the reports are checking in the synthesis and after the synthesis. So am I answered your query?
Yes, ma'am. Thank you.
Yeah. So I'll be just moving further with the clock tree synthesis. So I'm just to start off with the clock tree synthesis. Usually, what we will do in the clock tree synthesis stage means we will be trying to usually we will be distributing the clock signal. We will be distributing the clock signal evenly to all the sequential elements available in the design. So usually whatever the sequential elements are there in the design, for all the sequential elements, the clock need to be taken care. So that clock distribution will be, so the even clock distribution will be taken care in the clock tree synthesis stage. So what are the main goals of my clock tree synthesis? What are all the things I should need to be taken care in the clock tree synthesis for a better clock tree synthesis? So usually, three cases I can say. One, with the minimizing the clock skew, I can get a better clock tree synthesis, and even with the minimizing the clock latency, and even with the minimizing the clock transition time. So no need to worry. Actually, what clock skew, clock latency, I'll just take a next slide. I'll be defining each and everything. So usually, I should need to take care of minimizing the clock skew, clock latency, and the transition time. So what actually we were doing in the clock tree synthesis stage means, so usually here I am adding some clock tree constraints like latency, skew, clock skew or a max trends, max caps, all these, or even clock inverter, clock buffers, all these clock tree constraints I'm adding. Based on those things, I'm trying to build my clock tree, or I'm trying to balance my clock tree. So once after that, I'll be checking for the violations with respect to hold, because I have distributed now here onwards I'll be getting a propagated clock signal. So it is not a ideal one. It is a propagated clock signal. So I'll be checking here onwards hold violation. Violations with respect to hold I'm getting, any hold violations I'm getting, that should need to be taken care. As I'm telling, so clock tree building and balancing, right? So what actually building, what actually clock tree building I'm doing, what actually I'm doing the clock tree balancing. So building is nothing but I'm building a clock tree, or you can say the clock tree building can be done by adding or including the clock inverters, so that I can maintain the exact transition time, or you can say the duty cycle. So to maintain the exact transition or a duty cycle, I'll be adding I'll be adding or including the clock inverter to build my clock tree. So the clock tree building is nothing but I'm adding the clock inverters. As you can see here, I'm telling clock inverters, not a normal inverters. So the same way balancing means I'll be adding the clock tree. Usually the clock tree balancing is nothing but I'll be adding the clock buffers. So usually why I'm going with the clock buffers means it usually I'll be adding the clock buffers to meet the clock skew and the clock latency requirements. The skew and the latency requirements, to meet the skew and the latency requirements, I'll be adding building, clock tree building, and the clock buffers are added in the clock tree balancing. So usually you might be asking, what actually, why I am going with a clock buffers or a clock inverters instead of instead of normal inverters or buffers. Usually the normal inverters and buffers, usually that will not be used for clock tree building and balancing, because the clock buffers usually provides a better sleeve and a better driving capability when it compared to the normal buffers. That's why we were going with the clock buffers, not with the normal buffers. When it comes to clock inverters, usually I'm using the clock inverters usually because it will provide the better balance with the rise and fall times. And also it helps you to maintain the 50% duty cycle. So usually the clock inverters, why I am using means it will helps me to provide a better balance with the rise and fall times. Along with that, it will also helps me to maintain the 50% of my duty cycle. So that's why we were going with the clock inverter instead of normal inverter. So here I'll be checking with the hold violations. If any hold violations are there, that will be fixed in this stage itself. So moving to the how I can fix the hold violations, again I'll be going further with the optimization stage. So with the optimization stage, I'll be fixing the hold violations. So as I have already told, clock skew, clock latency. So I'm just listing out some clock parameters like a clock skew. So from usually what actually the clock skew means. So the clock skew is nothing but it is a difference in the arrival of my clock to the two consecutive clock pins of my sequential element. Here you can see source I have taken a PLL, that is a clock generator, and I am taking the two registers, that is a flip flop 1 and the flip flop 2. So usually clock skew is nothing but it is a difference in the arrival time of my clock at two consecutive clock pins of my sequential element. The sequential elements are flop 1 and flop 2. So it is a difference, or you can say clock skew is it is a clock arrival at a two different registers. So it is a delay or a difference in the clock arrival at a two different registers. If I am taking the example, you can see here from the pictorial representation, you can able to see the skew between the two flops. the flip-flop 1 and the flip-flop 2. You can able to see clock skew. So what is the difference I am getting? The clock 1 and the clock 2. You can able to see here. The clock skew means it might be a process variation, or even with the loading, whatever the loadings we were setting. So because of that variation or any unintentional mismatches in the design, there might be some mismatches in the design that may also leads to the clock skew issues. So that need to be taken care. So coming to the clock latency. So actually what a clock latency means, again the clock latency is the time taken from the clock source to the end point. So usually it is a time taken by the clock signal to travel from its source to the clocked element. You can say here the two registers here, the clock pin of the registers, the clock pin of the registers. So from source to the clock pin of the registers. So as you can see in the difference, the clock latency. I am taking the clock signal of a source, that is a clock generator, PLL, and the one clock I am considering, that is a flip-flop 1. So if I am checking the difference, you can able to see. That's where the clock latency comes into picture. So the clock latency is nothing. So source of my clock pin to the clock pin of my register, or you can say flip-flop. Here in the picture, you can see the flip-flop 1. So the difference or a delay between the source pin and source clock pin to the register clock pin. So this is all about the clock latency. And just moving further with the clock jitter also. Again, when the clock jitter again, it is mainly due to the temporal variations. So usually due to the temporal variations, the arrival time of my clock signal at the sink will create the clock jitter. So usually jitter is nothing but usually it refers to the temporal variation of my clock period. So and also the major sources for clock jitter is the dynamic voltage variation, or even with the temperature gradients, even because of the activity variations. Due to the activity variations, there might be a temperature gradient variation that may also leads to the clock jitter. Even with the jitters in the clock generators, what are the clock generators we are using? Within that clock generation, there might be a the jitter issues. You might be say clock jitter. So that may lead to the clock jitter. So the temporal variations or any temperature gradient or even with the dynamic voltage variations will leads to the clock jitter in the design. So usually what actually clock jitter means? It is the difference in the clock period between the two different cycles. For example, here I have taken flip-flop and the flip-flop 1 and the flip-flop 2. So what actually the clock jitter means? It is the clock jitter means it is the difference between the two clock periods. So for example, flip-flop 2 I have taken as an example here. Here you can see that the one cycle with a T1 and the second cycle with a T2. So the difference between these two, will give you the clock period difference between these two cycles will give you the clock jitter. So first I have listed with the clock skew, the difference in the arrival time with the arrival time of the clock at the two consecutive clock pins of my sequential element. When it comes to clock latency, again as I have already told, the clock latency is the time taken from the clock source to the end point. So again coming to the jitter, so it is because of the temporal variations in the arrival time of the clock signal at sinks usually creates the clock jitter, as you can see from the PLL generator. So usually the clock jitters comes into picture. So major sources of dynamic voltage variation. Jitter is nothing but the difference in the clock period between the two cycles. You can take any a register. So the difference between the time period, the difference between the difference in the clock period between the two different cycle will give you the clock jitter. So I'm just showing here one more example with the balancing, how actually the balancing will take place. So this is, you can see here in the balancing, before the balance and after the balance. So here the clock buffers are getting added into the design. As you can see here, these are the buffers added into the design. So that's why the clock balancing can be taken care. Usually why we were going for the balancing means it will give you the, or it will help you to meet the clock skew and the clock latency requirements. So that's why we were going for the clock tree balancing. So I'm just moving further, and one more thing, that is a non-default routing rules. So usually these rules will be added before going to the routing. So I'll be just moving with the next, that is a routing stage. So before start up with the routing stage, I should need to add the non-default routing rules, usually called as the NDR rules. So why actually we should need to add these NDR rules before the routing? So why can't we add in the routing stage? Usually when we were going with the default routing, so we can't able to fix the issues with respect to crosstalk or even with the electro migration. The crosstalk violations I am getting, any electro migrations violation I am getting in the routing stage, I might not be able to fix those violations if I am going default routing. So to avoid that issues, I will be adding the crosstalk or electro migration issues in the design before the routing stage. So this is all about the routing issues. As you can see, double the width, double the space. So again, the width and spacing for each and every metal will be taken from the .left files. So I'm just moving further with the clock tree synthesis. As I have already told, some clock tree constraints I am giving. First one is the NDR rule. Width, double the width, double the space I am giving here. These values will be taken from the .left, and I will be doubling those values. So here I have just chosen metal 4 and metal 5. Even you can start up with the metal 1 to metal 9 also. It's your wish again. So again, I am creating the routing usually the route types I am creating here. So to route the clock signals and all, I am making use of a clock routes. I am setting the clock routes constraints also. Along with that, building and balancing. So usually I will be making use of these constraints to set the clock buffers and the clock inverters to build and balancing of my clock tree. So along with that, if I have any clock gatings in the design, then I can add the clocks. If I don't have, then I'll be default one. This is from the library itself. So I'm just going with the default gate cells. Currently, I have not included any gate cells in the design. I'm just going with the gate cells available from the library. Once after this, I'll be creating this spec file. So again, when I am telling CC opt, CC opt stands for concurrent. CC opt stands for clock concurrent optimization. So when I am telling CC opt, it is a clock concurrent optimization. It is a technology which is integrated into will activate the best clock tree synthesis for your targets like power performance area of your design. Usually it will gives you or to activate the better clock tree for your design with respect to power performance area. So usually the CC opt is a clock concurrent optimization. It is a technology, the clock concurrent optimization technology, which is already integrated inside the Innovus tool. So which will help you or to activate the best clock tree synthesis, we will be making use of that CC opt tool or CC opt. Usually I'll be generating that file. I'm making use of a command and I'm generating the file. The file extension will be .spec. Usually we will call it as a CC opt.spec. Once after that, I'll making use of that file. So in the tool execution part, you can able to see. You can just open that file and you can able to see those things. So once after I'm loading that file, I'll be when I'm checking for the timing analysis. Once after doing the optimization, whenever the tool is doing optimization, backend it will be called with this file. So it will be calling with this file. Backend the tool is trying to call this file whenever we were doing the optimization with respect to the clock tree synthesis stage. So by this we can after the optimization I can able to fix the clock tree the set hold violation. Usually in the clock tree synthesis stage I'll be fixing the hold violations only. So if you want to generate the clock tree reports and all, I have just mentioned the command. Command used for generating the clock trees report and skew group report. This is all. These are the clock tree constraints which I'm mentioning in the terminal, and I'm checking for the clock tree debugger window. This is all about the clock tree synthesis. That's what I have just given in the pictorial. Read out. I think it is already about to. It is already more than a time I have taken. So I'll just complete with the routing. If any queries are there, you can just unmute yourself and we can discuss.
Ma'am,
So I'll start. Yeah.
one question is, what are the different techniques we can use to minimize the clock skew?
See, different techniques are nothing but what I am just telling. Clock tree building and balancing. Additionally, or even we have the option to whatever the constraints I am setting with the synthesis stage, predefined constraints. Here also we have in the clock tree synthesis also we have the options to modify those constraints. Based on the constraints also you can optimize skews and all. So you have some set of comments, whatever the constraints you are giving in the, you are mentioning in the SDC file, the same constraints you can just modify here with respect to the skew or even with respect to the latency and all. So with those things, I can able to optimize. Or even with usually the clock. Usually when I am telling clock skew means again I'll be taking care with the balancing. So balancing means again I'll be adding some clock buffers into the design where it will helps me to meet my clock skew along with the clock latency requirements. So one way with building and balancing, and even you have the options to edit or to modify your constraints based on the requirements to maintain your clock skew or a clock latency also. So any further queries?
No, madam, thank you.
Yeah. So now I am taking to the last stage that is usually called as a routing stage. So coming to the routing stage, what actually we were discussing. So usually routing means routing is nothing but we will be considering the complete logic, as I have already told, the interconnections, the complete, or else you can say the physical connecting or physical connections, the creation of the physical connections need to be taken care. So connecting the instances, whatever the physical connections with respect to the instance, that will be taken care in the routing stage. For example, I have some pins, signal pins, or it might be a standard cell pins. From one cell to another cell it is communicating. Then how I will connect those? Physically, how I will connect from one cell to another cell, or one cell to the pin, or from one cell to the to the clock signal, or from clock to the signal pins. So how I am connecting? So there the routing comes into picture through the metal interconnects. By making use of a metal interconnects, I am connecting all those physical connections with respect to the cell to cell or cell to pin. So where the routing comes into picture. Usually again we have a four stage process here. So before that I just want to list out some goals to be goals of routings. Usually to get a good routing database I should need to take care of these things. Usually one is with taking comes into picture. So that total, if the longer metal layers, it may takes up, it may not use a proper routing database. So the performance of the routing database will not be that much. To minimize the total interconnect or by reducing the wire length, I can get a good routing database. And even the probability, maximizing the probability, the taking care of the tool can completing the routing. So whatever the additional things I should need to be taken care. By probability is nothing but I will be taking care of the global net connections, all those things. So in the routing stage. So by that things also I'll be getting the good routing database. Or even the routing results will going to be a better one, or a quality of the routing will be better, or you can say the quality of the routing results will be good, which is acceptable to take. So and even so many lists are there, and even I should need to meet the timing DRCs, like usually I should need to meet the timing violations, and even with the DRC fixing also, and I should need to minimize the congestion hotspots also. Here also I am checking the congestion. In the placement stage also I am checking the congestion. After the routing stage also I will be checking the congestion. If any congestions are there after fixing from the placement stage, even still if I am getting any congestions in the after the routing stage, that congestion will also be taken care. So once after fixing with these things, I will be getting the whatever the quality of routing database or routing results I am getting, that will going to be a proper one. And even as I have already told, the signal driven, that is nothing but signal integrity driven. So the crosstalk noise, or even with a noisy delay, all those things can be reduced. By reducing those things or by fixing those things, I can able to get my quality of the quality of my routing results will be a better one. So next, the routing steps includes 4 categories, as I have already told. These 4 steps again done by default with a tool. First one is a global routing, track assignment, detailed routing, and a search and repair. So usually 4 stages we were considering in the routing. These things will be done by the tool by default backend. So global routing, what actually we were doing in the global routing. So global routing, usually it will try to avoid any congested global cells are there. So how by minimizing the detour, to minimize the detours, it will see is there any avoidable congested cells are there. So that is there any congested global cells are there in the design, that it will try to fix those things in the detailed in the global routing. Usually two stages. One is initial routing, where the connected nets are routed over the if any overflows with the G cells, that will be calculated here. Another one is a rerouting stage. So here in the rerouting stage, what happens means where the congestion oriented with the G cells, with any net overflows are there, that will be reduced by ripping off, or you can say by rerouting the nets. By rerouting the nets, that violations can be fixed in the global routing. So next one is a track assignment. I am just showing you the detail. As you can see here, the G cells what I am telling here. So the same way, I am moving with the next stage, that is a track assignment. Usually, when I am telling a track assignment, it will in the track assignment it will try to replace all the global cells. Usually, in the track assignment, what happens? It will replace all the global routes with the actual metal layers. Usually in this stage, where the routing tracks are assigned to each global route, each global routes, whatever the routes has been, the rerouting of net has been taken in the global routing. So for those nets, it will try to assign the tracks. It will try to assign the tracks in this stage. So usually assigning the tracks in vertical or horizontal portions usually taken care, or rerouting all the overlapped wires will be taken care in the track assignment. So next, moving to the next stage, that is a detailed routing. So in the detailed routing, it will in the global routing, it will also allocate the routing resources that were used for the connection. In the global routing, it will also allows you to allocate the routing resources used for the connection. So next, track assignment taken care in the global routing by assigning the tracks with the horizontal and vertical portions, horizontal or vertical partitions. Or once again, we will checking for the rerouting it on the overlapped wires. So next, coming to the detailed routing. So usually detailed routing, what happens means the complete design will be divided into a box. Usually we call it as a small box. Usually call it as a S box, or you can also call it as a switch box. So the complete design will be divided into a small box, usually which represents which is usually called as a switch box or a S box. So based on that, it will try to check for the all the possible DRC violations after the track assignment. And even in the track assignment, the track assignment will be done only once with the entire design. For the entire design, the track assignment will be done only once. So after the track assignment, we were coming to the detailed routing. In the detailed routing, the complete design will be divided into a small box. Usually we call it as a switch box or a S box. So using that, it will try to check all the possible DRC violations. It will try to fix all the DRC violations after the track assignment. And also after this, again, if any violations are, you can see here the DRC violations, as I have already told. It might be a shorts or minimum spacing issues, or minimum spacing issues, or is there any notch spacing issues with respect to IAS? That and all will be taken care. Spacing issues or minimum area spacing issues, minimum you can say all these spacing issues with respect to the metal layers. So that will be taken care and fixed these violations in the detailed routing. By default, all these things will be taken care. I'll be just giving route design command, or I'm just going to the route option. From the route, nano route, I'm telling tool to do the routing. The backend, these are the things the tool is trying to do. So next is last stage, that is a search and repair. So in the search and repair, what it will do, it will take the iterative process to fix the DRC violations. After the detailed routing, whatever the violations, all the violations fixed in the detailed routing, there might be a chances of remaining some violations which are not fixed in the detailed routing. So at that time, the search and repair stage, once again it will try to check the violations. Multiple iterative loops, it will try to check the DRC fixing. So the DRC violations will be checked and fixed with multiple iterative loops. So this is all about the physical design flow. So here where it will end. So if any queries are there, you can just let me know. So it is already exceeding the time, so you can just let me know, attend all the queries. We can just address as soon as possible and we can finish it up, so that I will be getting some break time for starting up with the tool demonstration in the afternoon.
Okay, participants, if you have any questions, unmute yourself and ask the speaker.
Yeah, actually, the physical design implementation phase is a vast, so many things are there. In a single shot, you might not be able to understand. Once if you start up hands-on practice and all, you'll get to know each and everything. So what actually we are doing in the each and every stage, whatever the 5 stages I have listed. So, like, no need to worry. If any queries are there with respect to each and every stage, you can just let me know. I'll be addressing.